All right.
Great, thank you, Yop. Like Yop said, my name is Anthony, and I'm in fact here in Amsterdam. So if you'd like to meet and talk, please let me know. I'm broadcasting to you live with Freek in the room with me. But yeah, so I'm a grad student at CU Boulder in Graham Smith's group. Halfway through my PhD, and before that, like Yop said, I worked at Rigetti. And I'm interested basically in quantum computing, quantum information, kind of quantum error correction, I think is where I'm going to go for the rest of my PhD. But today, I'm going to talk to you about the most recent project I've been working on with Graham and his group, which is on quantum sensing. So the title of the talk is Opportunities and Limitations in Broadband Sensing. Before I get started, oh great, you can see my mouse. I'd like to thank my funding. So NSF and NASA have funded me on this project, and then my co-authors are on the bottom left of the slide here, going clockwise from the top left. That's Jacob, Ariel, and Josh. Graham is on the right. David is on the bottom right. James is on the bottom middle, and Mike is on the bottom left. Everyone there is from Jilla except for Dave and Mike, who are now, they were at Honeywell, which has now been rebranded as Quantinuum after the merger with Cambridge Quantum Computing. So let's get started. Great. So I'll start with an outline. And also, I think Yop said this should be like an hour, so I'm targeting like 40 minutes. And then questions after. We'll see how that goes. So an outline for the talk, I'll start with a kind of model of the kind of system that we are going to be thinking about in this talk. I'll introduce the quantum Fisher information for anyone who's not familiar with it. It'll be kind of the operational definition of information that we'll be using to kind of talk about what we mean by broadband sensing. I'll give some examples of what the quantum Fisher information is for a few different kind of sensing protocols. I'll introduce the integrated quantum Fisher information, which is just going to be given by integrating over different frequencies. I'll then introduce a kind of discrete model of a sensing protocol, which we'll use to derive a few results. We'll show that many protocols actually have an IQFI of 2 pi t, where t is the duration of the sensing protocol. We'll have an interpretation of this, which I'm going to call no free QFI. So we'll see that in the context of broadband sensing, sensitivity in some kind of frequency band comes at the cost of sensitivity in other frequency bands. I'll give an example of a transverse field sensing protocol that actually surpasses this 2 pi t bound, and then we'll prove in general an upper bound on the integrated quantum Fisher information, kind of solidifying this no free QFI interpretation. I'll give a variety of a lower bound on the integrated quantum Fisher information for just protocols using pi pulses. And then I'll conclude with some applications. Great. And like Yop said, if you have questions, please just interrupt me. Let's get started. So the context for sensing in this talk that I have in mind, that I think you should have in mind, is just sensing a magnetic field. So the picture that I always have in my head is just a box that's a quantum sensor. You know it's a quantum sensor because there's an atom on it. And it's in a magnetic field, which I've written here as B. So you can just imagine the Hamiltonian B cosine omega t plus phi a phase Z. So it's just coupling via Z interaction, and we're going to ignore the phase phi for the rest of the talk. It should just add prefactors basically to anything I say, and we only really care about asymptotics in this talk anyway, so it's safe to ignore. This is a common Hamiltonian, as I'm sure everyone knows. If you have a spin in a magnetic field, it'll just precess. Something we'll see at the end where this is relevant is if you have kind of frequency noise on, say, a flux tunable transmon, that'll also just couple via Z. And so you can imagine fluctuations in the frequency of the qubit kind of manifest as this kind of Z-type coupling. And then at the very end, kind of another application, especially in the context of broadband sensing, is something like axion detection. And I'll say more about that at the end. Great. So I'll introduce the quantum Fisher information because I won't assume anyone knows the definition. So the quantum Fisher information is given like this. So say that we have a sensing protocol, you're trying to sense a magnetic field B at some frequency omega, and your sensing protocol has duration t, then the QFI is given as twice the trace of the square of the derivative of the state with respect to the magnetic field, the parameter being estimated. Yeah, like I said, B is what you're estimating, T is the duration of the protocol, and this somehow measures the information about the parameter. You can ask, in what sense does it measure the information about the parameter? There's an operational definition, which is given by the quantum Cramer-Rao bound. So in classical statistics, you have the normal Cramer-Rao bound, which lower bounds the variance of an estimator of a parameter of a distribution. The quantum Cramer-Rao bound does the same thing, just for a quantum state. So if you have a quantum state rho, which depends on, in this case, B is the parameter we're estimating, you can lower bound the variance of an estimator B hat by 1 over mj. So if you have a lot of information, if the Fisher information is large, the lower bound on the variance of an estimator is small. And m here is a number of copies of the state. So because it's like quantum, basically, you have to consume copies of the state in order to get information about the parameter you're estimating. Great.
Can I ask something?
Yeah.
The state rho depends on capital T, which I guess is the duration of the protocol. Do you mean the state at the end of the protocol?
Yeah. Great. So the kind of picture you should have in mind is that I have this box that's sitting in the field, and then I just let it evolve under the field with some kind of unitary evolution also on top of the field evolution, some control. And then at the very end, we just measure the state. So I'm not considering any kind of intermittent measurements.
Isn't that a bit weird? Because I can imagine that the state changes a lot over time, but maybe if it happens to not depend on the B field at the end of the protocol, but it did throughout the experiment, you would find that this derivative is 0, isn't it?
Yeah, that's true. So I'll give an example on like the next slide where the kind of distribution of the quantum Fisher information, like if you evolve for kind of an unfortunate period of time, you will end up with 0 sensitivity to the magnetic field.
Oh, so this is true. Okay, thanks.
Yeah, that's true. Exactly. Yeah. Great. Great. So some examples of just computing the quantum Fisher information. If your sensing protocol is you just take the qubit, you put it in the plus state, and you just let it evolve on a magnetic field, it's going to acquire some phase. The phase is linear in time and linear in the magnetic field. So I've drawn that on the right here. And you can just compute the QFI as I defined it on the previous slide. You just take the outer product of the states, you get 1/2 on the diagonal, you get phases on the off diagonals, and when you kind of square that and take the trace, you end up with 4t squared. So that's the quantum Fisher information of kind of the state here for DC magnetic field. If you have an AC magnetic field though, like, sorry, what was your name? I don't know your name. I can't see it on the thing. As the previous questioner asked, if you have an AC field though, it'll just oscillate in time. And so you can imagine that if you kind of measure the state at the end of the protocol, after it's kind of oscillated for a full period, you'll have 0 information about the magnetic field. And so I think the next comment I have here is probably going to say that, okay, so that's one way it can kind of zero itself out. Another way that it can explicitly zero itself out is if you instead have a protocol, rather than this free evolution where you do a single pi pulse, if that's your sensing protocol, then the picture now looks like what's on the bottom left here. So the blue line is the free evolution under the DC field. You do a single pi pulse as your sensing protocol, and then you continue to evolve under the DC field. Then you've echoed out the field. And then in this case, also the QFI at 0 frequency, so J of 0 is 0. If you do this protocol though, you will instead pick up some kind of AC sensitivity. So at a frequency that I think is pi over t, it might be 2 pi over t, I might have missed a factor of 2, you'll get kind of coherent amplification of the signal. And so if you have this single pi pulse in the middle, as the cosine turns negative and changes direction, the pi pulse will flip you to the other side of the Bloch sphere, and then you'll continue accumulating phase. So what this shows you is that in general, if you have some kind of sensing protocol, you'll have different sensitivities at different frequencies. This is perhaps clear if you've thought about things like echoing protocols, where kind of this is the whole name of the game. I'll talk more about that later. Great. Okay. So kind of given this discussion of different sensitivities at different frequencies, it's interesting to consider the integrated Quantum-Fisher information. So by integrated, I mean integrated over frequency. This is kind of a natural thing to consider if you're wondering if you have a sensor and you're like, how well, if I build a sensor, how well can it perform over a wide range of frequencies? Like, I just have one box that does sensing. Can I make it be good everywhere? So if you look at something like a Ramsey protocol, where you just put the state on the equator and let it process, and then flip it back up to the pole and measure, for instance, you do this in like calibrating a qubits like frequency, or sorry, the drive frequency for like driving qubits. What you see is that a Ramsey protocol has a peak sensitivity at DC, like we said before, of 4t squared. But the actual, if you compute the full kind of QFI as a function of omega, it's a sinc squared. And so kind of the characteristic width around the origin is 1 over t. And so if you integrate this, you kind of expect that you should end up with an integrated Quantum-Fisher information that's linear in time. And in fact, you do. And then it kind of dies off at high frequency exactly for this reason, again, mentioned before, that the field kind of oscillates and cancels itself out. Great. So for, I think the next few slides, or at least something that's useful for the rest of this talk, is imagine concretely for a sensing protocol that you have this model that's discrete. So you have instantaneous pulses, pi, so arbitrary unitary rotations, but they don't depend on the magnetic field, followed by periods of free evolution, ui, which obviously do depend on the magnetic field because they're free evolution. What I mean concretely is that you have a state like this that starts in plus, and then you have these kind of iterated uis and pis. I'd like to note also, as I was kind of making this talk last night, I was drawing kind of moving white boxes all over the place to cover things up and make the flow more natural. And I kind of felt like somebody writing like a ransom note with all the kind of cut out magazine pieces, because it's you can see the little lines on the top of the state there. So some handcrafted art for you. But so what I said is you have these n periods of free evolution, where the periods of free evolution are given by kind of minus I b theta z, where theta is just the integral of cosine. It's just integrating the Hamiltonian that I'd written previously. The final time Tn is big T, the total duration, and T1 is just 0. But then the Quantum-Fisher information depends on a derivative. If you just write out explicitly what this derivative is, you get this kind of phi term that's in purple at the bottom. You get down a theta j, and you also get down a z in this kind of string of unitaries. But then if you just work out explicitly what the functional form is then for the QFI in this case, for a pure state, I guess, you get this kind of 4 inner product phi phi plus inner product psi phi squared term. And this is kind of what we'll be looking at in the next few slides. And then a final note is that these thetas are kind of orthogonal in this sense. If you integrate them against each other, ignore the omegas that I've written there. That's just old notation. You get 0, but if you integrate them squared, you get pi over t times the interval, the duration of the free evolution period. And so actually this is explicitly why the Ramsey protocol I mentioned previously has an IQFI of 2 pi t, because it's in fact just the integral of this theta squared. Because when you, theta is just the sinc, it's the integral of cosine with respect to t. Great. So this is kind of a useful model to think about for talking about the integrated Quantum-Fisher information and the whole family of protocols, which are just modeled by these discrete sequences. So the first thing that you notice or first thing you can notice, when you start thinking about the broadband performance as measured by the integrated quantum Fisher information, is that many protocols actually satisfy that the IQFI is around 2 pi t. Like I said, Ramsey is 2 pi t, kind of for the reason I just mentioned. You integrate the sync squared and you get something that's proportional to t. In fact, any sequence of pi pulses has an IQFI of 2 pi t. So you might imagine that any of these kind of dynamical decoupling sequences you see in quantum computing kind of have an IQFI of 2 pi t, because often they just have pi pulses that kind of bounce you around the Bloch sphere. As an example, to kind of see that this should be the case with pi pulses, I've written a simple sequence of pi pulses on the right here. So psi is just, you start the plus state, free evolution, z pi pulse, free evolution, y pi pulse, free evolution, x pi pulse. This is actually simple to work through because the z just commutes with the u's, and then so I put a tilde over one of the u's when I commuted the y through, just because the z in the exponent picks up a minus sign. I had this pi here before, which is confusing for a number of reasons. So now I put in a little hat in Google Drive, which you can see. But so just calling that string of pi operators pi hat, which is also perhaps confusing because position and momentum operators, but pi hat is just a sequence of pi pulses that we're not going to care about. When you take the inner product of phi with itself, kind of the pi hat cancels, the z tilde here cancels. You end up with everything basically cancels except for these thetas. And like I told you, the thetas are basically orthogonal when you integrate them over frequency. Well, they are orthogonal. And then you just end up with the diagonal terms. The square of these theta terms is when integrated proportional to time. So you end up with 2 pi t. So this kind of argument generalizes to any sequence of pi pulses, and you end up with 2 pi t if you're on the equator. And I should also note that like starting on the equator is kind of the sensible thing to do for a lot of sensing protocols, because it's kind of the most sensitive place you can be to the magnetic field. This intuition changes a bit when you are considering integrating over frequency like we're doing, because you're interested in the performance on multiple frequencies. And we'll see that actually in a few slides. The last note is that kind of perturbatively, you also see that the integrated quantum Fisher information should be 2 pi t plus higher order terms, b squared t cubed. And so bonus slides for this talk, I had given this previously and I was running short. So I added in some extra math for all of you. So we'll look to see that you should expect kind of 2 pi t perturbatively for the integrated quantum Fisher information. What I mean specifically is we're going to move into the interaction picture for kind of the control we're doing. And then we'll use the Dyson series, considering that the B cosine omega term to be a perturbation, so weak magnetic field, for instance. And then we'll show that you should expect 2 pi t integrated quantum Fisher information. So the note that I've put here is just to show that this functional form I gave previously for the quantum Fisher information, this on the second line here, for phi plus psi phi squared, because psi is normalized, the derivative is 0. And that means that the real part of phi psi is 0, which means that the second term in the quantum Fisher information is completely it is negative, it's non-positive because it's a square of an imaginary number. All this to say is that when you integrate the quantum Fisher information, you can actually just look at the first term to get an upper bound. You can just look at this phi term to get an upper bound. So now consider a Hamiltonian where your control, so this is now looking at a kind of continuous control model, continuous sensing protocol. The G of t is the sensing protocol. It's the kind of unitary control you have, again, with this magnetic field that you're sensing in the background. Then if you just look in the interaction picture, your state psi is given as u, where the first u is just that's coming from the interaction picture. It's just the time-ordered exponential of the control. The second u is coming from the Dyson series. So I've written here, you just get some kind of Taylor-ish looking thing where the first order term is IB integral 0 up to t, where that little t actually should be the duration of the sensing protocol. And then the ZI here is the Z term coming from the second term of the Hamiltonian in the interaction picture. But, so if you take a derivative of this, like you need in the expression I have in the bottom right, you just kill off the first term and then the B goes away. And so this is the kind of lowest order term in the derivative. And so that's the derivative. I've just reproduced it on the top right. And so now if you just want to compute the integrated quantum-Fisher information, you can re-express twice the integrated quantum-Fisher information as this integral from -infinity to infinity of the QFI. But the point is that it basically looks like a Fourier transform. Well, no, sorry, it's not a Fourier transform. It's you get because you're integrating these cosines against each other, you get kind of delta functions. And that's the second line I have here. And then the third line, you end up with just two of these z's integrated against each other. But because they're z's, they just kind of square away, and you end up with 4 pi t to lowest order. So all of this to say is that if you perturbatively look at the integrated quantum-Fisher information for an arbitrary sensing protocol to lowest order, you get 2 pi t rather than 4 pi t because I introduced a factor of 2 on the first line. And then you get higher order terms that would be squared t cubed if you go to kind of next order in the perturbation theory. That was a lot of math. All of this to say is that if you look at it perturbatively, you get 2 pi t. And so the interpretation of this, kind of the first thing you should think of is that there's no free QFI, so kind of inspired by kind of a no free lunch type of motto. Sensitivity at one frequency comes at the cost of sensitivity at another frequency. So if you have a box that does sensing with some unitary protocol that doesn't depend on frequency, you put the box in the field, it does its thing, and then reports an estimate of a magnetic field. If it's very good at estimating the magnetic field at one frequency, it will necessarily, well, at least for these protocols with 2 pi t scaling of the integrated quantum-Fisher information, it'll necessarily perform worse at other frequencies. You might ask if there are protocols that have more integrated quantum-Fisher information, perhaps unbounded. As we'll show next, this is not possible. But as of yet, what we see is that at least for these protocols, sensitivity at one frequency comes at the cost of sensitivity at another frequency. Moreover, if you have short coherence times or weak magnetic fields, the perturbative argument tells you that 2 pi t is kind of the right limit to have in mind. And a final note that's interesting to note here is that it's known that optimal sensing protocols at a single frequency have sensitivity t squared. So Ramsey, for instance, is optimal in the sense of its DC sensitivity. It scales as t squared. What was not known to us prior to this work is kind of if you can make that sensitivity band, how large you can make it. Ramsey has this characteristic width of 1 over t, but you might wonder, can you have a kind of t squared scaling that over a constant width band, or like how wide can you make that sensitivity band? What I'll show you is that you can actually make that band, a constant width. So integrated quantum-Fisher information then of t squared. This is actually a protocol that has such an integrated quantum-Fisher information. So if you have just a continuous sensing protocol, where you have your control is just a transverse x field, so just gx. This is what I imagine it looks like. You just start in the plus state, and then you accumulate phase going along the equator from the z field, and then the gx control just pulls you up the block sphere, so you are probably oscillating kind of back and forth. You actually accumulate quadratically much integrated quantum-Fisher information in time. So I've given you some plots here showing this, plots at time steps 2, 4, 6, and 8. So the red curve around the origin, around 0, is Ramsey, which I've shown you already. It's like a sinc function. And so it has a very large peak around 0. It has very good DC sensitivity, but it's very narrow. That's the 1/t fall off I was talking about. Now, the green curve is a pi pulse at every time step. So the first one has 2 pi pulses, the fourth one has 4 pi pulses. And I told you before, I kind of argued that the integrated quantum Fisher information for that curve should be 2 pi t. What's interesting is that the pi/2 protocol I have here, which is doing a pi/2 pulse every half time step, actually has more integrated quantum Fisher information. If you look at the yellow curve, it kind of has the same peak as the green curve, but is it's thicker. It doesn't have these little dips going down. And that's perhaps not surprising if you believe the title of this slide, which is that the transverse field accumulates IQFI quadratically, because if you look at the GX curve here, you can kind of clearly see that it's very broad. So the area under that curve is, if you fit a line to kind of the series of plots, you see that it's quadratic. And the reason I say that the pi/2 then is not surprising is because then it's just a trotterization of this Hamiltonian. And so you should expect that if I do a pi/2 pulse every half time step, or a pi/3 pulse every third time step, 1/3 of a time step, that you would also accumulate quadratic IQFI. The kind of one way of showing that this GX protocol has accumulates integrated quantum Fisher information quadratically is you can kind of break up the sensitivity, the JOmega, over frequency. At high frequency, you can show that there's not much QFI, and then kind of around the peak, that's region 2 here, there's a peak around 2G, which you get just from looking at the rotating wave approximation, or just looking in the rotating frame, and then doing the RWA. Kind of when you drive on resonance, you can kind of see intuitively that you should accumulate QFI kind of quadratically. And so the kind of non-obvious part, I think, is the band around that peak is constant width. Great. So this is actually optimal, is I think one of the cool results that we have. To see that t-squared integrated quantum Fisher information scaling is optimal, I'll give you some of the like intuition. There's a bit more math you have to do to kind of make sure things work out, but intuitively, I already showed you this part. So if you again look at the functional form for the quantum Fisher information on a pure state, the second term, if we're only interested in upper bound, doesn't matter because it's non-positive. So this is, I think, the key insight. The integrated quantum Fisher information, integral JOmega, the first term on the bottom, is upper bounded by this phi. And phi is a derivative of the plus state acted on by a bunch of unitaries. When you take that, you're going to get a sum via the product rule of just kind of, I showed this on a previous slide, of just a z inserted at each spot in the protocol. So when you take that inner product, you end up with a gram matrix. The gram matrix is going to have 1 on the diagonal, but then also kind of order 1 terms on the off diagonals because it just comes from inner products of states. And so this V term here, which I haven't included just because it's not particularly elegant to look at, is a matrix with kind of order 1 numbers, which means it has eigenvalues of at most n. So then the integral is going to give you n times theta squared, where theta here is kind of a vector of the thetas I wrote previously. I told you that the integral of the theta terms is linear in time. So you end up with an upper bound on the integrated quantum Fisher information of 2 pi nt, where n is the number of pulses in your sensing protocol. But then we're kind of intuitively done, because if you have a continuous time sensing protocol, like I wrote before, with g of t is the sense of the sensing protocol, your unitary kind of control, Then you can imagine on the bottom here, what I have drawn is not me reinventing the integral, but rather me drawing out what trotterization looks like to me. So you imagine that you have your control protocol and you just break it up into time steps of size delta t. Well, how many are there going to be? They're going to be t over delta t. So putting in n is t over delta t, you end up with a kind of quadratic upper bound on the integrated Quantum-Fisher information. I said there were more details. There's more details because you have this delta t parameter now. And if you want a really tight upper bound, I suppose you take delta t small, but then the error coming from this discrete approximation would be very bad. So you need to kind of balance the two and push forward the error through the integrated Quantum-Fisher information. But in spirit, this gives you the quadratic upper bound. So quadratic in T is optimal, and we've given an example of something that is quadratic in T. Also, I don't have a proof in general of a linear in T lower bound on the integrated Quantum-Fisher information, but for pi pulses, it certainly is linear in T. But what exactly do I mean? If you have a single state that you're looking at, it can have QFI of 0, like we've kind of already pointed out. And you can have it at all frequencies, actually, because if you just do a single pi over 2 pulse up to the North Pole, your sensitivity at all frequencies is going to go to 0 because it's not sensitive to the magnetic field at all. But if you average over the initial state, at least for pi pulses, you can show that you accumulate integrated Quantum-Fisher information that's 4 pi over 3t. What this says, I don't know if I have another bullet on here. Yeah, what this says is that if you have a protocol that consists only of pi pulses, then there's also no free insensitivity. So it's kind of a converse result. Before it was, if you have sensitivity somewhere, you necessarily don't have sensitivity somewhere else. Lower bound like this says that if you have insensitivity somewhere, then you necessarily don't have insensitivity somewhere else, which matters for things like dynamical decoupling sequences where you want to suppress your sensitivity to noise at some frequency. At least with pi pulses, then that means you're going to be sensitive at another frequency. So that concludes the kind of results on integrated Quantum-Fisher information that I wanted to share. The next few slides are kind of on applications. So one of the first things that we had in mind when we were doing this is things where you're interested in sweeping over wide ranges of frequency. So one example is axion detection. I'm definitely not an expert in axion detection, but my understanding, I'm going to skip ahead to the end of the slide just so I can have this picture, is that one way people conventionally do axion detection is you have a cavity with some electromagnetic kind of profile. So there's like a large magnetic field. Axions come in, and my understanding is that axions couple to the electromagnetic field. So you're looking for kind of fluctuations in the EM fields of the cavity. And so you can imagine that having, thinking about broadband sensing of, in fact, electromagnetic fields is useful in this context. In fact, it's particularly useful because if you look at a couple of these references, depending on how optimistic or pessimistic they are, the estimates place a time for sweeping the relevant frequencies from a few decades to 200 trillion years. I took those numbers out of these papers. And that's just because the kind of frequency ranges, the frequencies where the axions can live are not constrained as far as I know. Moreover, you have some characteristic sensing time you have to do at each frequency. So one reason you would care about kind of these integrated Quantum-Fisher information results for axion detection is you can imagine building a different kind of sensor that's more broadband, which means you can sweep over kind of frequencies faster. And so what I mean in particular is if you imagine you have a sensing protocol on the right here, labeled by 1, that has height t squared and width 1 over t, which is kind of what Ramsey protocols have, but also what you might imagine a cavity has if the cavity has some kind of lifetime and your sensing maybe is inverse in the cavity lifetime, then that would take total time omega j naught to the 3/2, where omega is the bandwidth you want to search over. If you instead have something that's optimal in this integrated Quantumischer information sense of t² sensitivity and width that's like kind of constant, then you'll get a square root of j naught speedup, which is not exponential, as I think many people in quantum computing would like, myself included. But I think a square root speedup when you're talking at least 1 trillion years is a significant fraction of my lifetime. Great. The second place where these kinds of results are useful is in things like noise spectroscopy and dynamical decoupling. I talked a lot about pi pulses earlier, and that's what I'm familiar with dynamical decoupling. I see. In particular, you have, so there's spin echo, Hahn echo, which I've put the GIF here from Wikipedia. You have the qubit you put on the equator. If you have noise, it kind of decoheres out, but then if you flip it halfway through, you can echo away the noise. That's one way to kind of mitigate error when you're doing, well, to echo away error when you're doing quantum computing. But another way to do this is more general. So CPMG, Carr, Purcell, Mayboom, Gill, lets you suppress decoherence. So if instead you have a sequence of n pi pulses and you kind of bounce the qubit around on the Bloch sphere, you can cancel out noise at certain frequencies. And so I've put the kind of just like time, there's the sequential picture on the bottom and then a picture of the Bloch sphere on the top. But then there's also, this is a way to suppress decoherence, but then also CPMG is relevant in noise spectroscopy. So there is a description of these pi pulses as filter functions that you kind of integrate against a noise profile. And so the sensitivity of these kind of CPMG pulses looks like what I have in the bottom left here. Depending on the number of pulses and how long the sensing protocol is, you get these kind of little bumps in frequency space, which is maybe exactly the picture you would have had in mind for the integrated Quantumischer information. You know, Ramsey had this DC sensitivity, but if you kind of add more pi pulses, you can start echoing away DC noise and moving the sensitivity out. And these are all pi pulses. So in fact, the statement I made earlier about kind of no free insensitivity is true. If you are trying to echo away noise somewhere, you're going to necessarily be sensitive somewhere else. And so the last thing I have to say before I conclude is kind of, it's a thought that I haven't fully worked out yet, but the integrated Quantumischer information is somehow exactly what, it's very similar to this filter function that I just showed you. It somehow tells you about the sensitivity of the magnetic field. And so a picture you might have in mind is if you have some signal, which I've drawn here as a box function, basically with some Fourier amplitudes, then the quantity on the left here, so this is the part I haven't fully worked out. The Quantumischer information has units of 1/b², I believe, and the power spectral density, which is the kind of one of the experimentally relevant quantities that is reported quite often, has units of spectral density, power spectral density. So when you integrate this, it should be unitless. You can lower bound this quantity via the quantum Cramer-Rao bound, via the variances of the Fourier amplitudes. Those b's in the denominator should have hats on them. But then say there's a band that you're interested in. I've drawn that in the bottom here. So the signal is related to the power spectral density via something like a Fourier transform, which is why I've drawn a sinc-like function coming from the box-like function. But then you can lower bound this quantity kind of by the minimum variance on the band you're interested in, integrated against the power spectral density. You can upper bound the quantity on the top left just by pulling out the maximum. And then we know that from what we discussed earlier, that the integrated Quantumischer information is upper bounded by t². So ultimately you get this picture where if you integrate against the QFI, you can kind of say something about the sensitivity in a band times the, by kind of multiplying by prefactors related to the integral of the band you're interested in. And I think probably what's relevant here is that the if you integrate the power spectral density, for instance, of like a wide sense stationary function, you end up with the variance. So somehow the integrated quantum Fisher information is exactly or is related to in some close way. Again, I haven't worked this out completely, to the filter function I provided you on the previous page, where it tells you about the QFI tells you explicitly about the sensitivity in a region, but very likely you can treat it as some kind of kernel to integrate against. But with that, I want to conclude. So just as a quick review, since I'm supposed to tell you what I'm going to tell you what I want to tell you, and then tell you what I told you. We talked about a model for kind of the sensing protocol you should have in mind. We introduced the QFI, did some examples, introduced the integrated quantum Fisher information overall frequency, introduced a discrete model, which was useful to kind of show that many protocols have 2 pi t integrated quantum Fisher information, which let us give an interpretation in terms of no free quantum information. Sensitivity at one frequency comes at the cost of sensitivity at another frequency. But this discrete model also let us kind of prove an upper bound on the integrated quantum Fisher information. We gave the example of the transverse field, which saturates this bound. We said for pi pulses, you at least kind of have linear sensitivity when you integrate over all states. And we concluded with some applications where thinking about this is not only theoretically, but kind of experimentally useful. And I would like to conclude by saying thank you. Again, thanking my funding agencies, NSF and NASA. And if you want to reach me, I'm at Polloreno at most places. And as I've been excited to share, I own the phone number 1 I fit qubits.